All right, the next concept in this class is something that's new. Typically, this is a concept that I would not discuss in past years, but I've decided since to change that, mainly because in past years I wasn't covering it, and it is part of the Wisconsin State Science Standards. And looking at them, I thought since not everybody takes AP Chemistry, it might be a really good idea to start talking about energy and the role energy plays in chemical reactions. Now, we've already talked about the law of conservation of mass. When we balance a chemical equation, we have to make sure that the amount of mass in grams on one side of the reaction is equal to the amount of mass on the other side. And the way we can make sure that happens is that the same number of atoms is present on both sides of the arrow. And that is following the law of conservation of mass. There's also a second law that is followed, and that is called the first law of thermodynamics, which is the law of conservation of energy. In the law of conservation of energy, energy is not created or destroyed, it simply changes form. So when we look at a reaction, there's a specific amount of energy that goes into the reaction, and there's a specific amount of energy that goes out of the reaction. And the difference in those values, this difference in those two values, will then give us the amount of energy that is either expelled or absorbed by the chemical reaction for it to occur. All right, so we're going to look at how energy plays a vital role in looking at chemical reactions and how when we mix some chemical substance together, they feel cold, and while others we mix chemical reactions together and they get very, very warm or hot, okay? And that has to do with the amount of energy that goes into the reaction and the amount of energy that comes out of the reaction and the difference of those two values. Energy is not lost, it's not created. It simply just transforms, forms, and if there is a intake or outtake, that's why the surroundings will either get colder or warmer based on what the chemical reaction is. Now, before we talk about energy diagrams, we need to talk about something that's called collision theory, which is a vital concept in the AP Chemistry exam as well. If I have A reacts with B to produce C, in order for A and B to react to form C, they have to collide with each other. The thought is, in this theory, is that a molecule of A and a molecule of B must bash into each other for them to effectively produce products. And if they don't collide, then product formation is not favorable. Now, the number of collisions that occur and how often they occur are all factors into how quickly the reaction will be. And that's talking about chemical reaction rates, kinetics of reactions, how quickly they occur, are they slow, are they fast? And that's something we'll talk more about for those of you who decide to take AP Chemistry. For now, for a product to form, the reactant molecules must collide with each other and in order for products to form. Now, not all collisions will be successful, and there's two reasons why. First of all, take a look at this diagram here. Okay, the top one we have an effective collision, and the bottom one we have an ineffective collision. Looking at the diagram, can you identify one factor as to why not all collisions are successful? What has to be true in order for there to be an effective collision? And the first one we talk about is the orientation of the collision. Here, for this molecule of Cl2 to form, Cl bonded Cl, this free Cl atom had to hit by the other Cl atom in the molecule, NOCl. If it doesn't hit there, now this bond cannot form between the two green chlorines to form Cl2. When it bonds, this other one can dislodge, and we have successful formation of products. In the second collision, the Cl molecule collides with the oxygen molecule and therefore cannot form the molecule Cl2 like we see in the top one. And there, either two things can happen. Either they can bounce off and nothing happens, or we could have had the green molecule and the red molecule form, and with that, Now we have a chemical compound of ClO, which would then be a byproduct. It'd be a product that's not wanted or desired, and so we could also have a different reaction take place where we form different products. So first of all, the orientation of the collision, the molecules have to collide in the right spot. Now, the more complex a molecule becomes, the less likely this molecule, this atom, is going to collide in the right spot. The bigger and more bulky it becomes, the chance of it hitting the proper spot gets less and less likely to occur. So usually here, what this tells us is the simpler or smaller the molecule is, okay, the collision will be more likely to occur. The orientation of the collision will be more likely met. So the bigger the molecule becomes, the more spots of where the collisions could occur increases, and therefore the chance of it hitting in the correct orientation gets less and less. Okay? There's a second factor, and that is the collisions must occur hard enough. If they collide in the right spot, they don't necessarily form products either. They have to collide hard enough. Why? The collision is what provides the energy to break the bonds of the reactants. The reactants have to break apart. In essence, the Lego set has to be disassembled before a new creation can form. So before new bonds can form, the old bonds have got to break. So the reactant molecules must collide hard enough for their bonds to break. And if they are able to break their bonds, then the products can form. And when the products form, bonds form. So the old bonds break and the new bonds form if the collision hits hard enough. So two things have to be met for a product to form. The molecules must collide in the correct spot. Certain atoms might have to hit with certain atoms. And they also have to hit hard enough that they break the bonds of the current molecule so new ones can form. And this is what I talked about before with the energy in and out. Okay? To break bonds is energy in. Energy's got to come into the molecule, and that is coming from the collision. And then when new bonds form, energy comes out. And the difference in those two energy values will tell me if the reaction will give off heat or will absorb heat, and therefore we have something called an endothermic or exothermic reaction. All right, turning the page. So now we're going to look at what's called an energy diagram. In the energy diagram, we're going to look to see what happens here in this chemical reaction. So in a typical energy diagram, we're going to start off with a specific energy value, which is labeled with an R. And this is going to be the energy content of the molecules. How much energy does each of the hydrogen and fluorine molecules have? And that is going to be given by the vertical axis position, which is the energy. So where this starts is going to be the energy content of the reactants in kilojoules. Think of those bonds. Those bonds possess a certain amount of energy, and with that, that dictates where these reactant particles start off in this energy diagram. Where the diagram ends is the product. Okay? The bond forms between hydrogen and fluorine. It's a single bond. Actually, all of them are single bonds. So a hydrogen-hydrogen bond has to break, and a fluorine-fluorine bond has to break in order for an HF bond to form. Here we can see that where we start, the amount of energy, and where we stop, the amount of energy, they have different energy amounts. And that's because the bonds associated with each of these molecules has a different energy associated with it because it's a different type of bond that forms between different elements. Each bond has a different energy associated with it, and therefore the location of the reactants products will be in different spots. So this reaction, these energy profiles, look at this. The start of the reaction is where the energy content is of the reactants. Where it ends is the products. And the graph ends up looking like this. You'll see a hump that will then end at the end. Okay? So let's say, for example, that the reactants have an energy content, and this is measured in something called kilojoules. It's an energy quantity measurement that we often use in chemistry. Let's say this starts off with 30 kilojoules. So the energy content of the reactants is 30 kilojoules. The energy content of the products is 50 kilojoules. The products possess more energy in their bonds than the reactants do. So you'll notice that the graph causes a peak to form. The height of where we start to the peak, this is the amount of energy that has to go in to this reaction in order for it to occur. And then from that peak down to where it stops is the amount of energy that comes out of the reaction. So the energy in is this has to be the amount of energy it has to take to break the HH bond and the FF bond. This is how much energy it takes to break the bonds, is to go from the reactants to the peak. And then when bonds form, they release energy. And they release energy because they've become more stable. As free atoms, they're not as stable as molecules. So when they bond and they reach their octet, they become more stable, and therefore energy is released as those bonds form. So in this case, the amount of energy in is greater than the amount of energy out for this chemical compound to form. And therefore, when I subtract the two, we get a difference The difference in the height of the products to the reactants is given as a value which is called delta H. And delta H is called enthalpy. Enthalpy is defined as the heat that is either released or absorbed per molecule of reaction. Okay? In here, if we go through the mathematics of it, okay, in order to figure out the amount of energy, we always subtract the out from the in. Okay? So 50 kilojoules minus 30 kilojoules gives us a total of 20 kilojoules. So the enthalpy of this reaction would be positive 20 kilojoules. Positive 20 means that the energy overall from start to end, we've gone up by 20 kilojoules. So there's 20 more kilojoules of energy possessed in the products and the reactants. So whenever the products end up higher than where the reactants start, this is an example of an endothermic reaction. When delta H is positive, when the products are above the reactants, the reaction is endothermic, and energy has to go into the reaction. More energy has to go in order to form the products. And what happens here is then because energy is coming into the reaction, it's absorbing energy as the products are formed. This is going to make the surroundings feel colder. When this reaction occurs, to your touch, it's going to feel cold because energy is being pulled in. Just like when you step outside right now in the dead of winter, it feels cold outside because energy is being pulled away from your warm body to go into the surrounding air, which is much colder. And because it draws energy away from your body, you feel very, very cold. Okay? And that's what happens in endothermic reactions. Exothermic reactions are the opposite. They make the surroundings feel hotter. So an exothermic reaction, like if you use a hand warmer, if you go ice fishing or hunting or just outside in the wintertime, if you have a hand warmer, they feel warm because they have an excess of energy that is being liberated out to the surroundings. Again, the difference in height of the products to the reactants is called enthalpy. Okay, so here I've got a couple examples of diagrams you might want to chart down. Again, here I see the difference in the products to the reactants. This difference is the enthalpy of the reaction, which is going to have a positive number. Sometimes they also say delta H is greater than 0, which means it's a positive value, some number. Whenever you have products above the reactants, we know immediately that this is an endothermic reaction. So energy is going to go in to the reaction for it to occur. Energy has to keep going into it to keep forming the products because they have a higher energy content than the reactants do. Okay. One other thing about this graph. Now, first of all, what would be the enthalpy of this reaction based off of the vertical axis values given to you? Again, to find the enthalpy of the reaction, we take the energy content of the products minus the reactants. So 90 minus 50 gives me a value of positive 40 kilojoules. The enthalpy of this reaction would be positive 40 kilojoules. Again, a positive value indicates that it's an endothermic reaction. One other thing we notice is the energy in. The energy in for this reaction is to go from the start to the top. And let's say that this energy in is 140 up here. So to go from 50 to 90, go from 50 to 140, 90 kilojoules of energy had to go into the reaction. And then from 140 down to 50, 50 kilojoules of energy came out of the reaction. And if we add those together, we also get a total of positive 40. So that's another way of looking at it. The amount of energy in versus to break the bonds. Again, this is how much it takes to break the bonds. And this is the amount of energy that it comes out to form the bonds. Okay, and based on the amount of energy in, we're going up positive 90 or coming back down 50. The difference is positive 40 kilojoules. That's another way of looking at how to figure out the enthalpy of the reaction in terms of energy in and out. Okay, and we call this energy in AP chemistry class. This is called EA, which is called the activation energy. The collision, in order for products to form, the collision must occur at or above the activation energy requirement. So for this top graph, the collision must occur with an energy of at least 90 kilojoules or higher. If the collision only occurs at 80 kilojoules, we don't get high enough to overcome the activation energy. We have not successfully been able to break the bonds, and products cannot form. So again, in collision theory, we have to hit hard enough. So if we don't hit at 90, if we can't get to the peak, we can't go over the peak. So we've got to hit at 90 kilojoules of force or greater. Any collision that occurs below 90 will be an unsuccessful collision. Okay? Vice versa, if the products are below the reactants, this is an example of an exothermic relationship. So now, the difference in height of the reactants to products, the products have an energy content of 10 kilojoules, minus the reactants has an energy of 60. Subtracting, we get an enthalpy of negative 50 kilojoules. So whenever we have a negative value on delta H, this indicates that it's an exothermic relationship. So 50 kilojoules of energy come out of the reaction, and they go into the surroundings, and that energy is in the form of heat, and this is why it feels warm, or it warms the area around. It feels hot to the touch because it's releasing energy, because the products are more stable than the reactants, and energy comes out when they form. Again, the amount of energy that goes in, the activation energy, let's say the peak here is at 100, just for example. So 40 kilojoules came in to get to the peak, then 100 down to 10, 90 kilojoules came out. So positive 40 in, negative 90 out. We get a difference in energy of negative 50 kilojoules, which is exactly the same energies we had before. And this is the amount of energy that is expelled to the surroundings. So these are energy diagrams and how we can use these energy diagrams to quantify how much energy is released or absorbed for a chemical reaction to take place. Okay? Now what I'd like you to do is I have some different energy profile diagrams that I'd like you to go ahead and solve and work on as your homework. One other note that I'd like you to look at here for a second is sometimes the reaction doesn't occur in a single collision, but it might occur in multiple collisions. Okay. If on an energy diagram you don't have one hump, you have multiple humps, what that means is the reaction occurs in a series of collisions. So the first collision goes from the energy content of the reactants to, I'm just going to label this as I, is the intermediate part, the middle part. The first collision is the substances forming this middle step, and then the second collision is that middle step forming the product step. So these energy diagrams can have more than one hump. Each hump indicates how many collisions. So a two-hump energy profile diagram tells me that the reactants have to undergo a series of two collisions to form the products. However, the enthalpy of the reaction is still dictated by the start to the stop. The difference in height of the reactants to the products is still going to give me the enthalpy of the reaction. Okay? But from the reactants to the first peak, this is the amount of energy in for the first step, and this is the amount of energy out for the first step. And then we have the amount of energy in for the second step and the amount of energy out of the second step. So if I look at the amount of energy in and total it and the amount of energy out and total it, I would get the same number if I simply look at the difference in height of the reactants and the products. But each collision, you'll notice, causes the energy always to go up because we got to first break apart the reactants of step one to form the products of step one, and then the reactants of step two have got to break apart. So we always go up in energy first and then come back down, because energy in, we have to break the bonds, and then we have to make the bonds. And bond breaking is endothermic, bond making is exothermic. All right, so now I'd like you to analyze some of the homework problems. It should not take you very long to do this, but I have some different energy profiles that I'd like you to analyze and answer questions about, and that'll be part of your homework leading into the last homework example, which we'll talk about next week, where we look at bond energies. Okay? Again, I appreciate you listening to this lecture, and I hope you're understanding a little deeper level of endothermic and exothermic reactions, and now you can do the homework fairly well. Okay? Again, the only thing this week left to do also is to take the quiz on balancing equations and identifying type of reactions. If you haven't done that yet, please go ahead and make sure you get that done for this week. Thank you.